All attendees are in listen-only mode.
So good morning, everybody. This is the iROC Technologies webinar. Do I really need to worry about soft errors? So if you're here for something else, then you're in the wrong place. My name is Paul McLellan. I work with Semi Wiki these days. I've been in semiconductors for 30 years or so. But actually, this whole area of single event errors and so on, reliability in general, is an area that I don't know that much about. So I'm going to be talking with Adrian Evans. He's the principal engineer here at iROC. He's 15 years of experience in verifying complex ASIC for network applications, mostly at Cisco, where he co-led the reliability, availability, and serviceability team for chipsets inside Cisco's core routers. And then when he left Cisco, he joined iROC and is active in the soft error research community and standardization and stuff like that. So before we get started, a few housekeeping items. So firstly, you guys are muted to avoid background noise, so you can talk as much as you like. We're not going to hear you. We're going to we'll do about 30 minutes for the webinar, including some Q&A at the end. If you want to ask questions, just type them in the questions box, but we basically won't answer them during the webinar itself. We'll leave those and have a Q&A session at the end. So, Adrian, let's start on the assumption that not everybody on this webinar actually knows what soft errors are and how important they are and why they need to sort of know more about them. So why don't you just sort of give us a little introduction, a soft introduction, as it were.
Hi, Paul. Sure. Let's start with a little overview of what actually causes a soft error. So a soft error is triggered by a subatomic event that could either be a neutron or it could be an alpha that's emitted from packaging materials. If it's a neutron, then the neutron has to hit the nucleus of an atom in the chip, typically a silicon atom, and cause charge to get deposited around a transistor. When that charge gets deposited, it can create a voltage spike, and that can cause a soft error effect. So broadly speaking, soft error effects can be categorized into sort of three categories. The one that most people think of is single event upsets. That's an upset that affects either a flip-flop or a memory cell and cause a stored bit to flip from either 1 to 0 or 0 to 1. We can also get that charge that got deposited. It can create a current pulse on a combinatorial gate if the transistor that gets struck is in a combinatorial gate. And that current pulse can propagate down through the logic, and there's a chance it will get captured. And the other final kind of soft error event that's to some extent the most serious one is a single event latch-up event, where the implicit thyristor that's present in a CMOS gate can get triggered, and it creates a short circuit, and that single event latch-up condition will persist until the chip is powered down, unlike a single event upset or transient, which doesn't actually damage the chip in any way.
Things that soft error rates are going down, but I've also heard that as we go through process nodes going down 28 nanometer, 20 nanometer, 16, and so on, the problems are getting worse. So which is it? Are things getting better or are things getting worse? Do we have to worry about this, or it's just going to get better on its own?
That's a good question. So if we look at the soft error rate per bit, it is trending down with smaller and finer technology nodes. And part of that is just caused by the fact that the area occupied by a flip-flop or a memory cell is that much smaller, so the target is that much smaller to get hit. And also we're seeing that with the transition to new FinFET transistors, generally they're less sensitive to soft errors. But really, that's only half the story, because as you know, what's also happening is Moore's law the number of transistors on a chip is growing exponentially. And the probability of a failure in a chip is roughly the product of the number of bits and the per bit failure rate. And if we combine those to sort of build a per chip failure rate, that's we're showing now that's actually increasing. And I think over the longer term it's going to continue to increase, but there is some kind of intrinsic maximum, because a given, if you have a die of a given area, there's only so many neutrons or so many alphas that hit that area in a unit of time, and that sort of provides kind of an upper bound on the soft air rate. So eventually, as process technology nodes go forward, there probably will be a plateau that will be reached. Oh, sorry, and there's in the graph I showed you, there's one thing I did want to also highlight, and that is that although the per bit soft air rates are trending down, the multi-bit upset rates are still sort of constant or increasing. And nowadays, so a multi-bit upset occurs when in a memory, one particle strikes the chip and causes the value to be upset in two or more adjacent memory cells. In the picture on the screen, you can sort of see some of the patterns that are possible when a particle hits a memory. It can be either horizontally, vertically adjacent, or even just nearby cells can be upset. And this is a significant phenomenon because it's become quite common practice to use error-correcting codes on memories that can correct single-bit errors. But when we're getting these multi-bit errors, we need to look at other solutions than just single-bit error correction. And this is also exacerbated by the fact that chips today often have on the order of 100 megabits or more of embedded SRAM.
You mentioned fit rates a couple of times. Can you remind us or tell us what is a fit?
Sure. A fit is a failure in time. So one fit is one failure in about 10 to the 9 hours. Now, you might look at that and say, well, 10 to the 9 hours is a long time. My product lasts 10 to the 9 hours. I'm good. But I think you have to do the math and think about it. So if let's say we have a chip that has 200 fits, which is, could be a system on chip today that's in that order of magnitude kind of failure rate. If you have a system that maybe has 10 chips in it and you have 100,000 systems, then you could be looking at on the order of 150 soft error events per month. So that sort of just sets the scale that it is not completely negligible.
So tell me how this sort of works through the whole flow, right? So this this cosmic ray incoming neutron, and my router fails. So how do we get from that initial event that almost at the atomic scale all the way up to my system fails and reboots or whatever happens?
So the first thing that there's in the chain of events is that we have a subatomic event, whether it could be an alpha particle or a neutron, and that causes charge to be deposited on sensitive areas of chip around a transistor, and that can cause a memory cell to get upset. That could be a flip-flop or a memory bit, or it could be one of those transient pulses that we saw earlier, and that causes an incorrect value to get into your more complex digital circuit. And then eventually that incorrect value, depending on whether that's a packet, it could be a data that's being returned to a microprocessor, it could be the program counter of your microprocessor, and that has an effect on your system. And you can imagine if it's something like the program counter on your microprocessor, then it's going to have a big impact. And the impact really highly depends on what the system at hand is. Silicon devices are being used pretty much everywhere nowadays, and if that chip happens to be in something like a a medically implanted device, like a pacemaker, the impact could be significant. In an automotive control system, if that error happens to be in the program counter of your anti-lock brake system or your steering system, it could have a really significant system level impact. I also mentioned aerospace systems. Those are have specific challenges to soft errors because of the high altitude where those systems are used. There's the neutron flux, the number of neutrons hitting the circuit is much higher, and that can cause more errors. And again, also in sort of compute and telecom applications, if the error causes an outage on the network or it causes a server to crash, that can have an impact on a service level agreement that has a financial impact if this system is out.
So we live on a planet where, we're bombarded by cosmic rays all the time. So obviously not every one of these soft errors causes, the system to fail, or, nothing would stay up for very long at all, and our computers and cell phones and everything would be crashing all the time. Is there something that sort of mitigates that?
Yes, indeed. There are many masking effects that cause the soft errors that occur to be blocked, or the soft error events to be masked. For example, if you look at the low circuit level, if we have an upset, let's say in a flip-flop, and that's feeding a 2-to-1 mux, and the branch of the mux is not selected, the one that had the error, then the error is gone, and doesn't propagate downstream. Or a slightly more subtle form of masking is what we call temporal masking, which means if you imagine that the upset, we have to look at where the upset occurs relative to the clock edge, and if the upset occurs early in the clock cycle, as you sort of see on the picture, then the corrupted value that we've shown in red, has time to propagate through the downstream logic and get sampled. You can imagine if the soft error had happened just a little bit before the clock edge, it wouldn't have had time to propagate, and it would have gotten masked also. So those are kind of low-level masking effects, but there are also higher-level masking effects that we often call functional masking. So you have to think about what system you're dealing with. I like to think of a video application. If on some kind of video application the soft error just causes a single pixel to get inverted, no one's ever going to know. If it causes a whole frame to get dropped, well, it's perceptible, but probably not a big deal. But if it causes the whole stream to lock up, then that's bad, and that will have real-world consequences, and you could have business consequences. Again, different applications, you have to look at what the effects could be. In a networking application, it could be minor, something like a single packet being corrupted, or it could be as extreme as a whole rack of routers crashing in the extreme case. So, there's the whole spectrum from the error being masked at the lowest level to it triggering a very severe impact at the system level.
So I'm an SoC designer, say. Obviously, there's nothing I can do about shutting off cosmic rays hitting my chip. So what do I actually do about it? What do I need to worry about? And how do I know whether I've got a problem or I don't have a problem?
Well, if you want to find out whether you have a problem, it's quite common practice in the industry to test chips at accelerated radiation test facilities. These are places, special laboratories, which are able to produce an accelerated neutron flux, where they can create a neutron flux that's on the order of 100,000 or even 1,000,000 times higher than the natural flux. And you can design a test where you put your chip, or perhaps several instances of your chip into that beam, and you observe the effects. And then you obviously you'll see a very large number of soft errors in that kind of environment, but you can scale back the results to normal environmental Earth conditions and see how your chip will actually behave. You can also test for alpha particle sensitivity, using radioactive sources that you put adjacent to the die and that emit alpha particles at a much higher rate than you would naturally be exposed. And again, that's another form of accelerated radiation testing. Now, another, here we see that when you want to do this accelerated radiation testing, it's quite a setup. On the left of the screen, you can see we have a radiation experiment where we have many boards stacked in a row that are going to be exposed to a neutron beam, and then we obviously need test equipment to monitor the boards. We need to, of course, provide power to power the boards, and we have to log all the results in a very careful way so that after those results can be analyzed and a fit rate associated with the chip. And doing this kind of neutron testing is, a lot can go wrong during the neutron testing if you haven't planned for it, and that's a kind of experiment where experience makes all the difference. And another basic thing that, important thing that people need to consider when they're designing chips is the packaging material. Is that the alpha particles, the contribution of soft errors from alpha particles comes from the materials that are in close proximity to the die, typically solder bumps. And it's important that chip designers specify very high quality materials that have a very low alpha emission rate, and potentially that manufacturers perform alpha counting on those materials to validate that their suppliers are really meeting the alpha emissivity rates that are being specified.
Well, that's great, but testing chips after we've designed them is all very well, but in general what we need to do is to design chips that don't have these problems, or that we can measure measure how big a problem we have ahead of time. So what can we do at design time rather than after manufacture?
Right. Well, it's important to include soft error analysis into the design flow up front, and there's two parts to that. The first part, and it's very important, is there's soft error rate prediction. Now, predicting the effective or the visible soft error rate of a complex chip is not an easy task. You need to consider it at the cell level, sort of to understand, given the particle flux that's present, in a terrestrial application, at what rate am I going to see upsets in my flip-flops? At what rate am I going to see glitches in my gates? And then you need to think about what's, once we've established that at that sort of flip-flop or gate level, what's the effect on the system? How much are those masking factors going to block the soft errors? And how many soft errors are still going to be, propagate up to have visible effects? So there's sort of a two-phase approach, a cell level and a system level approach to prediction. And this, this isn't something you can really do back of the envelope. You need dedicated EDA tools that can calculate the cell level effects and then can compute the system level effects. Now, if you're lucky, you do that prediction and you find that your chip is meeting the fit rate that you want it to meet. So you find about it. Now, the two most significant contributors to soft error rates in most chips are the memories and the flip-flops. Now, using EC standard practice, but as we talked about earlier, multi-bit upsets are a concern. And one thing that can be done is selecting memories that have increased interleaving so that the bits that are physically adjacent aren't in the same logical word. But there's some limitations to that. You can't always increase the interleaving, especially on small memories. We also can, we're starting to see an increased use of stronger than single error correct ECC codes in memories, error correcting codes that can correct 2-bit errors or sometimes more in order to deal with these multi-bit upsets. The other thing is that you need, in memories, you need to make sure that the memories are scrubbed. What that means is that if you have a single bit error that occurs and you do nothing about it and it sits in a memory location that doesn't get written, and then maybe 2 years later your product's still up and a second single bit error happens in that same memory location, you now have a 2-bit likely uncorrectable error. So it's important to make sure in the background you have software to go through and find those single bit errors and clean them out. And in addition, softwares are not the only source of reliability problems in silicon. We also have bits that have permanent failures during the lifetime due to effects like NVTI. And we need to make sure that those two effects, which are lifetime effects and the soft error effects, don't interact in a way that defeats the error correction. Now, switching over to flip-flops, flip-flops are the, if you will, the second most significant contributor to soft errors in big chips. And there do exist flip-flop designs that are hardened against soft errors, except these flip-flops are typically on the order of 2x the area of a traditional, simple D-type master-slave flip-flop. So what we need to do is try to apply a small number of those hardened flip-flops in the most critical state locations in the chip in order to significantly reduce the likelihood of a significant failure in the chip without adding too much area or power overhead.
So it sounds like some of this stuff depends pretty critically on the process and maybe the manufacturing, the whole approach to manufacturing, whatever. So what data should I expect to get from the fab? If I'm a fabless semiconductor company and I'm going to TSMC or Global or some foundry like that, then what should I expect to get from them, and how do I use that data?
That's a really good question. So fabless companies need to work with their foundries and their library providers to obtain quality SER data. Now, what makes this challenging is that that data isn't a single number. It's not just you can ask them what's your fit rate for your flip-flop and get a number back and you're done. Fit rates depend on a lot of factors. For example, if you have 2 different flip-flops in your library, they're going to have 2 different fit rates, most likely. The fit rate is going to vary with voltage. The fit rate is going to vary with the state stored in the cell. So, it's not a single value. It's kind of a whole database of values that you need to get from your foundry or library provider that characterizes the soft error rate of their technology. A little bit like, you can think of it a little bit like timing data. You can't just ask your library provider, give me the one number that characterizes the timing of this gate. You need to get a whole characterization of the timing versus voltage versus load and other factors. And when we talk about alpha fit rates, it also gets quite complicated because we have to understand, the emissivity in the packaging materials and also serve what the package and what the space between the materials that are emitting the alphas to the actual sensitive area looks like. And the other thing that's really critically important is when you're asking a vendor for SER data, ask them what the error bars are. If they don't know what the error bars are, you got to wonder, do they really have a good handle on the data? So really, you have to be savvy when you're asking for SER data. And yeah.
So this SER data analysis sounds horribly complex and maybe expensive. And is it just something I can kind of ignore, or is it really worth my investing in doing this kind of analysis? Is it something I really need to do?
That's a key point. And I think people need to think carefully about the economics of reliability. There's clearly a cost associated with performing accurate SER or any other reliability analysis on a chip, and there's very real costs associated with mitigation, whether that's ECC, hardened flip-flops, and those costs come in area and especially in additional engineering costs. And so it is tempting to try and cut corners. Initially, when I like to think that there's some sort of optimal level of reliability for a given application. And as you start to cut corners, you're going to sort of increase the number of errors that happen in the field. And you know, depending on the application, that's going to have an increased field return rate. That's going to have a cost. One of the things to bear in mind is that often when a soft error event occurs in, let's say, a server card or a router card, you know, there's no clear diagnosis saying, oh, a soft error happened in the flip-flop, that's a good card, just reset it and leave it. You know, there's some kind of crash in the system, it's unexplained, the customer is unhappy. A typical procedure in that situation is just to replace the card, and you know, and you never know really what happened. And that kind of background unexplained return rate has, you know, has a real cost to a system, to the end system company. So as that rate gets higher, the costs increase. And then at some point, you know, if you're really sloppy in your design, if you're designing without ECC on your memories, you're not worrying about your packaging materials, you sort of get into an area where you're going to have a catastrophic kind of failure, where you're going to get into a product recall scenario, and that's where you really don't want to be, because the costs can go through the roof, and you know, could really ruin you. But the other thing to consider is that that you know, if you invest too much in reliability, if you're going to great lengths to put mitigation features on your chip that maybe you don't really need, but maybe you're doing that because your analysis wasn't that accurate and your quick analysis sort of told you that you have a problem, when maybe a more refined analysis would show you don't have a problem, then you're getting into the over-design scenario, and your chip may not be competitive. It may have, you know, a higher power consumption than the competitor, or you may just be late to market because you were fiddling around with reliability features that fundamentally aren't necessary. So, you know, I feel the key thing is that people need to make at least invest enough of an investment to understand where on this reliability curve they sit, and you know, if they really need it, then they can look at implementing mitigation. And the other thing that I want to, you know, draw your attention to in terms of reliability, which is a little bit different from other areas, is you know, a system is only reliable as its you know, weakest component, or the component with the highest failure rate. So just, you know, as a silly simplified example, imagine you have a card with 4 chips on it. If one of the chips has a fit rate that's 50 times higher than all the other ones, you know, if your team that's designing, let's say, chip B is off fiddling trying to make the fit rate of chip B go from 35 to 34, where you've got another chip on the card that's got, you know, over 5,000 fit, you're wasting your time, because it's not going to make any difference in the system reliability. So one of the things that we, you know, feel is very important is for manufacturers of complex systems that have lots of silicon on them, they should seriously consider doing accelerated radiation testing of the entire system, so that they can identify the weak components and focus their investment on the, you know, the most sensitive components in their system.
iROC's not a huge company, so how do you work with your customers and you know, both, well, through the whole sort of fabless ecosystem, from foundries to, you know, fabless companies to, I don't know, packaging company? I'm not quite sure even who's involved these days.
Well, you're right. That iROC isn't a huge company, but iROC is a company that has assembled a set of experts that kind of bridge the entire base of knowledge that's needed to analyze soft errors. You know, you kind of saw from the presentation that it's understanding the whole chain of effects from the nuclear, you know, reactions at the subatomic level all the way up to the impact at the system level requires a very broad span of knowledge. Now, some big companies, you know, an Intel or an IBM, they have dedicated software teams that where they made that investment to have that knowledge fully in-house. But typically a fabless may not have a full team like that with the full set of knowledge. And iROC helps those companies integrate with a sort of entire ecosystem to perform software testing, software analysis, and software mitigation. We have very close partnerships with pretty much all the key foundries in terms of working with them to analyze the intrinsic soft error rates of their technologies. We have relationships with fablesses where we work with them to provide that soft error data that comes from the foundries and to help them analyze their complex chips. We also work with system houses who may have in-house soft error teams or may need to augment their teams with either test services or with SCR analysis for complex chips. And we're also a very big player in terms of radiation testing for standard components as well as complex components. And we kind of provide the interface to the radiation test facilities. It's not always easy for a company to show up at a radiation test facility at short notice and do their radiation testing. But through iROC and our close relationship with the test facilities, we can arrange for radiation testing of components at relatively short notice.
So any of you out there have questions, then feel free to type them in the question box, and we're sort of entering the Q&A phase now. In the meantime, I'm going to toss Adrian a real softball and say, tell me a little bit more about the actual analysis tools you guys have, what they do, and sort of how you use them, when you use them in the design flow, and so on.
Sure. We have iROC has two tools that we provide for soft error analysis. As we saw earlier, there's sort of two steps: a cell level analysis, which is addressed by our tool called TFIT. TFIT is a tool that takes as input a cell, which could be a memory cell, a flip-flop, or a combinatorial cell, and it also takes a model of the process technology from a foundry, and then it performs a series of detailed circuit simulations to compute the fit rate of that cell. And the TFIT tool is used by many major foundries to characterize the soft error rate of their of the libraries they provide, as well as many library providers. The second tool we have is called SoC, or System on Chip Fit, and this tool takes the output of TFIT, the intrinsic soft error rate from the cell, and then tries to compute what's the system level effect. And it's able to compute those masking factors like the logical masking factor, the temporal masking factor, and by fault injection, the functional masking factor, so that you can sort of compute, I have X million flip-flops in my chip, I have X 100 megabits of SRAM, and I know this is a technology failure rate. Therefore, I expect that once a month or whatever occurrence rate, I'm going to see a visible failure in my chip in its normal application.
Sorry. Once the fit data has been characterized by TFIT, how do you sort of get the error bar, and then so how does that flow through into the sort of SoC fit numbers and measurement?
How do the error bars propagate? That's a good question. So the TFIT tool is based on a response model, and in preparing that response model, there are certain limits on the accuracy that can be achieved that we internally are aware of, and we work with our customers to communicate those sort of limitations on the error bars that of the computed fit rates. And we try, when we work with customers using the SoC fit tool, we make them aware of those error bars on the intrinsic fit data, and we work with them in terms of the trade-offs on the analysis they do using SoC fit to obtain the level of accuracy they need. Often what we find is that a customer, an SoC fit customer, has a target they're trying to meet. I mean, as an example, if they're trying to say, I need to meet a fit rate of, let's say, 100 fit. If the output of SoC fit shows they're at 30 or 40 fit, then we're pretty confident that they're going to meet their 100 fit target. If the output of SLC fit's getting much closer to 100 fit, let's say it's showing 80 fit, then what we usually do is go through and refine the analysis in order to either bring in the error bars or we would recommend mitigation in that case.
And obviously the reliability of a system depends sort of on what the system is, right? There's a big difference between my cell phone crashing and my ABS system crashing in my car. So how do those kind of reliability numbers get pushed down from essentially the system people or the sort of end users of all the way down into the rest of the ecosystem?
That's a really good question, and that's one of the hardest parts of reliability analysis. And that really comes from the system architects. I think in the medical devices community, there are fairly well understood targets that need to be met. In the CPU or high performance computing community, there's also fairly well understood targets that are established for individual CPUs. In other markets, it's driven a little bit more by economics. We were talking about field return rates. You can associate a cost with a returned card, and you kind of work out what's an acceptable return rate that we can tolerate without it becoming too expensive. Some common sense says you don't want the #1 cause of field returns of your product to be soft errors, because that's clearly that's a cost you don't need to incur. So if you can keep the field return rate due to soft errors, let's say a step below, whether that's an order of magnitude, a factor 2 below the field return rate due to other causes of failure, then you've kind of made sure that soft errors aren't the weakest link in your reliability chain.
Okay, we have a couple more questions, but I think we'll answer those by email because we're sort of out of time. So thank you all for attending. iROC Tech is at DAC next week if you're in Austin, booth 1738. And, of course, they have a website, iroctech.com, where there's lots more information. And, obviously, you can call them or email them, and they will respond and work with you. So thanks for coming.